Welcome, folks. So again, this is a discussion on MATLAB Simulink-based field-oriented control, and then we have been discussing field-oriented control approaches in our past videos and how to simulate them using MATLAB. We looked at steady-state models, dynamic models, and then looked at how we can generate position signal information for this kind of simulation work. Now, this is actually building upon what we have discussed last time, basically using the same model and then extending that to include the dynamics of the dynamometer side. Now, if you remember from our last simulation, we didn't have a dynamometer or any mechanical inertia considered in our implementation. Essentially, we assumed that we had a position sensor signal or properly speed regulated with very high bandwidth, and therefore our speed was constant, and that was used to generate our position signal to establish field-oriented control and drive this motor model. Now, that might look a little bit more unrealistic to some of you. So there was a request in the channel asking, okay, how do we implement the inertia aspect and then get some realistic simulation developed? Okay, so this video is actually trying to provide that information. So we are using the same model as before. Now, instead of the difference here is, instead of using a speed, assuming that your speed is regulated, we have our torque signal fed to another Simulink model which contains the mechanical dynamics and the DC motor. Okay, and then from that block we generate the speed signal and we integrate that speed signal to obtain the position. So essentially this is the DC motor speed controller and the mechanical dynamics, and we'll have to set those up and we'll go through that in a little bit here. Now, so if any of you would like to look at the theory part of this, I have a set of videos, set of lectures on this concept, so please feel free to go review that. That's why I'm not showing any material, any equations in this video. Okay, so here, if you can see, we are setting the current references in this block, and here in this we set the speed reference. Okay, we set the speed reference, and then this is our current reference. Now if we go into this DC motor model, these are very familiar equations. Okay, so if you look closely here, this is our motor model. This is our motor electrical circuit, electrical equation, inductance and resistance. We have our back EMF term, which is a function of speed here, right, KE, and then the rest of this is your closed loop controller. So initially, so this is a cascaded controller where we have our current regulator first, which is generating the voltage, and then the input to the current regulator, or the reference to the current regulator, is from the speed regulator block. Okay, so we have the speed regulator feeding the reference to the current regulator, which is in turn driving the voltages and then generating torque. That torque, along with the electromagnetic torque from the PMSM, is what causes the speed, and they're actually subjected to the mechanical dynamics. So we have our inertia and windage, or the damping constants here, and they pass through this in resulting the speed. So if you, this is what I mentioned, there's a good set of lectures on this topic, so please feel free to go through them. And then I discuss how to design current controllers and very simple speed controller. There are other sophisticated speed controller designs in literature, but in the videos I discuss a very simple approach. And then so that results in the speed, and then in this block we basically integrate the speed and then take the remainder just to create the sawtooth waveform that goes into our PMSM for field-oriented control. Okay, so it's quite straightforward. And if in case some of you have questions, so these are the same PMSM parameters that we had and the field-oriented control parameters. And then for the DC motor, I use these parameters. These are just parameters from another motor. These are the mechanical dynamics. These are the speed controller gains. These are the current controller gains, in case if you want to try this yourself. And then this is actually a faster simulation too. Don't have to worry that much. If you run this, it'll run relatively fast. But I'm just going to show you the results here. Here you can see my current IQ and ID currents and how they are being regulated. Okay, so initially they are 0. This is where our speed reference is being set, and then currents are being regulated to 0, and then this is where we apply our current reference, and then you can see the currents being properly regulated to 2 amperes on Q axis and 0 amperes on D axis. Now if you go into the speed controller, the dyno side, you'll see that we apply a step input of 100 RPM, and that should be shown here. You can get this size. There we go. So this is your current reference that's been speed reference that's been injected, and you can see the speed is regulated. And then when the current PMSM current step change comes in, there's a little bit of a dip in the speed because this is a non-ideal system simulation, and then you have the controller again responding and regulating that speed back to the normal 100 RPM reference. And then you can look at the DC motor torque variation here. Okay, if you look at the DC motor torque variation, that should match closely with what the PMSM is applying. And then if you want to look at the currents, you can look at this signal here. Ultimately, if you want to see what the PMSM torque output looks like, again, it's going to mirror your Q-axis currents, because basically we are modeling a non-salient machine. Okay, so I think this hopefully gives all of you some good idea of how to implement this dynamometer setup, and then you can actually simulate different cases, different research work, and then include or add different elements to this the simulation to make it, cater to what you need done. Okay, I hope this helped. Please let me know if any other questions you might have, any other topics that you'd like to cover. Next time I will be going over how to implement the inverter for PMSM controls, replacing these gain blocks here. Okay, all right folks, thank you for watching, and look forward to seeing you in another video.